This is a flip video about thermochemical equations, or we can call them reactions. And today we're going to be talking about enthalpy, which is also known as heat of a reaction. So to begin, chemical reactions involve bonds breaking and bonds forming. So let's take a look at this example here. And on this side, I've got my reactants. And if you notice, I've got methane, carbon bonded to hydrogens, and I've got chlorine, right? Remember, chlorine's diatomic. And so over here, in order to make the products, I need to break these bonds, right? So if I notice over here on this side, my product is now going to have a chlorine attached to part of that CH complex. I've got to break off that H, and I have to break the chlorines apart. And then on this side over here, I have my remaining H and chlorine formed together. So in this instance, these bonds breaking actually require energy to be absorbed, and the new bonds forming give off energy. So my reactants right now in this situation are absorbing energy, and my products are releasing it. So we've moved from just talking about changes casually to, in this video, talking about chemical reactions, where we actually make new products. Okay, so now let's take a look at that topic one more time. And that is, again, the important takeaway point is forming bonds releases energy. Breaking bonds requires you to add energy. So in a chemical reaction, therefore, right, this means therefore, it's shorthand. In a chemical reaction, there's energy involved on both sides of the equation, okay? What is this energy involved in both sides of the equation called? Well, it's called enthalpy. And since we're looking at one side as the reactants, the other side as the products, we're actually interested in the change in enthalpy. And so again, another way of saying change in enthalpy is, it's a fancy name for the heat of a reaction, right? So this reaction, or we can actually look at a generic reaction. This reaction right here, let's say, I've got my reactants A plus B, have some sort of a heat associated with it. And let's just, we'll take that generic H right there for heat. Remember, heat, H. And let's just say that the H is 2 on this side. We're just being hypothetical. And on this side, the H is 1, okay? So these are the heats of the reaction, but in our case, we want to always figure out the change in enthalpy. Remember, change in enthalpy. So we don't use E, we use H to represent the heat, right? But this represents change in enthalpy, which I wrote here. Triangle means change. So I hear change, and what does that mean mathematically for me? Well, remember, change means a difference, a subtraction. So all I have to do is take my heat of my products and subtract them from my reactants to figure out what's the overall heat for that reaction, right? What's the overall enthalpy change, or the heat of the reaction? Enthalpy change and heat of reaction are the same, okay? So if I take a look here again and apply this equation, I know my products have a heat of 1 and my reactants 2. I can subtract those from each other. So here we go, right? 1 minus 2, and I get a negative 1. So my change of H for this reaction, again, my enthalpy for this reaction is negative 1. Or in other words, my heat of my reaction, that this reaction's heat associated with it, its overall change is negative 1. Okay, well, what does negative mean? And is it possible to have a positive change in H? And the answer is yes. So let's take a look at that. A negative change in H meant that that reaction was exothermic. So let's bring that back and look at it. So when these two combine to form that product, therefore they released more heat than they absorbed, exothermic. So the surroundings became warmer. All right, and a second ago we said, is it possible for reactions to have a positive change in H, a positive enthalpy, right? A positive heat. Sure, this reaction isn't, but there's definitely others that can be, right? So after the subtraction's done, I would see a positive difference, and therefore it's an endothermic reaction. Now, the way these chemical reactions will appear, or where you'll see that change in H put, so let's get ourselves a nice clean paper, is you will see that A plus B yields AB. So I'm just using that last reaction. And over here on the side, you'll see the change in H written on the same line. And it says change in H is equal to, and then maybe ours is -1, and our unit will be kilojoules, which is a unit of heat or joules. So that's -1 kilojoules. So in a thermochemical equation, right, bringing back to the main point of the video, it's an equation, chemical equation, and that has heat written on the same line of that reaction. So this reaction, now I can look at this and say -1 means exothermic. This reaction is an exothermic reaction, okay? Now, I can also write my heat in a different way. So let's take a look at another format, and that is A plus B yields AB plus, and I can actually put the heat, right, amount here in kilojoules on the right-hand side, right? The right-hand side are the products. So I show heat being released. I was supposed to say released. Okay. I hope you can write the rest. So this is an exothermic reaction. It shows heat released. I'm supposed to say released. Okay. All right. Well, what if my reaction is endothermic? Well, let's do that one. So if my reaction is endothermic, we'll just give a slightly new reversed reaction. Okay. And let's say this is endothermic. I can write it like this. Just put the heat off to the side with my positive number. So let's just say 1 kilojoule. Again, that's just for the sake of this example. Notice it's positive. Or I can write it, now remember in endothermic, heat is absorbed, right? So in this instance, I'm actually going to insert heat into the equation. So I'm going to put that 1 kilojoule here in the front plus my AB yields A plus B. So notice in this instance, the heat was put as a reactant. So when my heat is a reactant, it's endothermic. These are two different ways to express the same idea. So this is one way to do a thermochemical equation, and this is another way. These are both endothermic, okay? Now, again, let me bring back what it would look like if it was exothermic. In exothermic, the enthalpy, or the heat of the reaction, again, will just have the negative sign, okay? And again, what would it look like if I was going to write this exothermic like this? I would literally put it on the correct side. And so A, B, right, plus, and now this is where it gets kind of tricky, 1 kilojoule. Oops, right? And so you ask yourself, why is that a plus if this is a negative? Because the way you write these is that this plus sign can be considered like A and B react to form this and this. But the fact that it's a product, I know it's exothermic, so when I use it in further lessons, I will make sure to put a negative sign when I use it. But when I write it out, it stays here just as an and. So don't think of this necessarily as a positive. Think of it as an and. So this and this is made. So these are our two different types of chemical equations.